erosion in those high entropy alloys, and maybe what is the correlation. You mentioned also the aluminum and cobaltum nickel alloys. How is that better resistance?
Yeah, sure. If you don't mind, I'm gonna share my screen.
For sure.
Can you see it?
We
Right.
can see it. Yeah, definitely. So
Okay.
for good morning, good afternoon, or good evening, depending on when you are watching us. And thank you for being with the Material Business Podcast. My name is Monica Hernandez, and I'm your host. And I have a really special guest today. Wandong, thank you so much for coming to our podcast.
Thank you so much. Thank you for inviting me.
So, we're going to talk about a lot of things that are very interesting for metallurgists and people that work in the materials realm. So, we're going to talk about erosion and materials, and a little bit we're going to touch on how is this realm of, you know, research, and specifically in those areas, how is that is going, and then how do you see that advancing? Um, I had the privilege to watch Wandong in one of her presentations in the University of Alberta in Edmonton some months ago, and that was really nice. So
Thank you.
that's how we got connected. So that's how connections happen, and that's what we see and we speak a lot about in our podcast. So thank you for accepting the invite. I'm gonna go ahead and read your bio. So Wandon Wang is a PhD candidate in material science and engineering at the University of Toronto, under the guidance of Prof. Yuzu, focused on the study of wear and erosion. Wandong is investigating the wear performance of medium entropy and high entropy alloys. During her studies, Wandong collaborated with Weir Group and NRSERC, which is, I guess, one of the government's agencies, right? And aims to uncover the mechanisms driving the wear resistance in new materials. Wandong and her colleagues are committed to advancing their findings to address practical challenges in material durability. And that's what we all want to see, the connection between academia and industry. So why don't you start by telling us why do you want it to do this material science and then study all this research on PhD material science engineering, and specifically this very subject of wear?
Thank you very much, Monica. Thank you for inviting me and give this warm introduction. So my interest in material science and engineering started during my undergraduate studies. My major was metallurgical engineering at that time, primarily related to fabrication of iron and steel, which are still widely used materials. At that time, I was fascinated by the effect of compositions and annealing treatment on material properties. For example, it's very interesting that when you add some chromium and aluminum content in the alloy system, the material going to show good resistance to oxidation. I think the curiosity of about how microstructural changes translate to macroscopic phenomena in the real world inspired me to pursue a PhD. So at the beginning of my PhD, thanks to our group, I get a chance to collaborate with an industry partner. So they focus on wear and erosion. Basically, they offer the products and design to their mining customers to help enhance the productivity. So they sent us some worn parts, and at that time, I can directly see the effect of wear, and also I understood the financial impact of wear in the industry. So, due to relative motion, wear can change the geometrical shape of the component and also reduce the operation efficiency. So, the cost to simply replace or maintaining those parts could be very high. We have to keep in mind that wear cannot be avoided at all. It can only be reduced, right? There are many ways to reduce wear. For example, you can add some lubricant into the frictional system, or you can change your design. So, from my side, I wish to understand the mechanism and develop new materials to reduce wear. Thank you so much.
That's amazing. And you have just done the exact thing that I was always, and I am always stressing how everything that we're studying connects with industry and what is the financial impact and how is this. And you have touched in a very good point is you said I was able to see the wear, how it looks like, how it is
Exactly.
impacting. So that is very important. So for everyone that is listening to us, this is the importance of having collaboration ongoing. And I'm very glad that we are now getting more interconnection between industry and academia so we can see the real life examples. So you explained a lot on wear and erosion. It's my understanding that you work with the high entropy alloys. Can you explain that erosion in those high entropy alloys and maybe what is the correlation? You mentioned also the aluminum and cobaltum nickel alloys. How is that better resistance?
Yeah, sure. If you don't mind, I'm gonna share my.
For sure.
Can you see it?
We
Right.
can see it. Yeah, definitely. So for
Okay.
everyone that is looking in or is listening to this podcast in Spotify, she has some amazing slides. So go to the YouTube so you can see everything that she is going to present. Go ahead, Wanda.
Thank you so much. So, to be honest, there are limited reports on the application of entropy alloy or like medium entropy alloy in erosion. Some of the studies focus on one or two testing conditions, but erosion is not an intrinsic property, which means that the erosion rate will be affected by the testing conditions. For example, we change the particle velocity or we change the impact angle. Even if we change the particle we used, let's see, we change it from aluminum oxide to silicon carbide, the result may also change. So before I explain the why we choose these high entropy alloy, I think I need to talk about what is the dominant factors for a good erosion resistance. So, what is erosion? Erosion describes these phenomena that small bodies, or what we call erodent, repeatedly impact the surface. So basically, they're gonna eat the surface in small bites. So there is a misconception that people think when we talk about wear and erosion, a hard material always behaves well. It is true in some situations, but for erosion, it's not. It's not that like that. So there are two mutual actions happens during the erosion. One is the cutting action. The other is the plastic deformation. These two actions will be affected by the impact angle we can see from here. So at a small angle, there is a great possibility of the cutting action, which means that a hard material, a strong material, performs well. At a high angle, like here, materials with good ductility resists the impact by plastic deformation. So in a summary, if we wish a material to perform well at all angles, we need it to be both strong and ductile. So why we choose high entropy alloys? Why this one is perfect for this application? So the year 2004 marked the new era of the in the design of high entropy alloys. So basically, high entropy alloys consists four or five or more than five elements, and the contents of each element are e- is equal or in a large proportions. So there are many studies focus on high entropy alloys from like they talk high entropy alloys from different aspects. So what we focus is the mechanical properties. So this Ashby plot shows the this actually plot of fracture toughness versus yield strength prove that compared to other major material classes, high entropy alloy exhibit excellent strength ductility balance, and this is why we think that it could be a good candidate in erosion application. So let's narrow down to see the aluminum, copper, aero, nickel, the material used in this study. So the microstructure of this material is dual phase. So it contains a soft phase, which is the FCC phase, the phase center cubic, and the hard phase, which is the intermetallic compounds, the B2 phase. To study their mechanical properties, we introduce the high-speed nano indentation mapping techniques. Uh, it helps us to understand to study the mechanical property, especially the nano hardness and the indentation modulus across these phases. So we can see the result that the it shows a distinct property. So the design strategy behind this research is to exploit the distinct property of each phase. The soft phase, which is the FCC phase, is intended to accommodate plastic deformation, which is particularly beneficial at high angle. And the hard phase, which is the B2 phase, is used to resist cutting action. So we hypothesized that the dual phase HEAs can show a better resistance to erosion. So this is the material design for this project.
Wow, that's amazing. And thank you for walking us through the process. So we have, some sort of background of what goes behind and which one of the phases specific work in this particular alloy is. So that really helps us put together the pieces. So doing this work, what are some of the most findings like surprising or like, oh wow, we didn't expect that this happened, or some of those things that were unexpected or that you uncover through your research?
So I just wish to give the audience the basic logical flow why we choose these materials. What is the design strategies? So we do have some interesting findings after the erosion test. First of all, is the erosion rate, which is the mostly concerned and mostly like important important parameters. We performed the test at five different angles and used the model to feed the collected data. And the results show that entropy alloy do they exhibit a better erosion resistance compared to stainless steel at all impact angles. And this model can also help us separate the two aforementioned action, the cutting action and the deformation action. We can see that The HEA show a comparable resistance to plastic deformation, but it has a better resistance to cutting action. So this is why it shows a better resistance compared to stainless steel. We also wish to understand the erosion mechanism and also those features changes with the impact angles. So we use the SEM, the scanning electron microscopy. So we can see that at a normal angle, there are main two features. One is the embedded erodent, the other is indentation craters. Due to the large vertical component of the particle velocity, it may penetrate the it allow the particle to penetrate deep into the surface. Those particles may stay there, act as an embedded particle, or they may leave an indentation craters. The former ones may also be removed uh, due to subsequent impact. So when we incline the angle to 20-degree, so there is like due to the large horizontal component of the particle velocity, it drags the particle to move forward. So we can see this leap formation at the exit point of the particles. We also perform some cross-sectional analysis to understand the deformation mechanism just below the eroded area. Under the mutual effect of heating and high strain rate deformation, the dynamic recrystallization is triggered. So we can see like for stainless steel, it shows a relatively uniform deformation zone. But for the dual phase HEA, we can see that uh, a refined and elongated FCC lamella here, but the hard B2 phase remains to keep its original shape. To further confirm our assumption, we also did some EBSD analysis to see the strain distribution. Here is the result. We can see that from the misorientation map, the FCC lamellae bear more plastic strain under a normal impact angle. We can see from this single FCC lamella, the misorientation change a lot within several micrometers. So this result um, proof that HEA, the dual phase HEA, can be used for the in the erosion condition, and also it revealed the role of each phase under the particle impact. I guess that's the those interesting findings.
Yeah, fantastic. And is this all of the research has been completed through your work and the work of your colleagues, I guess, at the university, right?
Yes.
Perfect. So, how do you envision this piece of research being applied to solve any, like, where can we apply this research? Because in the wear and erosion, there are multiple, like I can think at least of 10 on the top of my head applications that we can use it, but where will you see this type of material could be applied in in industry?
So the potential application for this study is the gas transportation. The velocity of the erodent used in this study is about eight varies from 80 to 200 meter per second, depending on the compressed air we used. And the erodent in this study is the aluminum oxide, which is the worst case hard erodent. So basically, the material being tested in this study is in a relatively harsh conditions, and the results show that HEA can lead to the lead to the improvement of the lifespan of the component. So by improve its durability, we can reduce the frequency of maintenance and replacement of the sectors. And therefore, we can decreasing the cost, reduce the financial impact of wear. So I have to say that this research is still in lab scale. It's complete. It finished. It finished in a lab scale test. Looking ahead, I'm hoping to integrate these findings into commercial applications, so we can further adjust the compositions and also maybe introduce some treatment like thermal treatment or hot working, cold working to finally adjust the properties for specific requirements. And would be better and suitable for certain application in industry. And also, the insight gained from this research can help with future material design, especially for like erosion application. So maybe we can use this HEA as like as a matrix, and we can add some ceramic particles and the hardener to further improve their erosion resistance.
So I guess this is just the tip of the iceberg for collecting and making it a sustainable product that will ultimately make any of our industry challenges
Yes.
facing where an erosion being one of our candidates for more sustainable production, I guess. And so it's very interesting. I think it has all the components that we'll like to see when we see our research. Is we've looked at real examples, we've looked at different options, and then we've looked at how this will impact and how that will reduce any of those issues that potentially can be. But also you're looking ahead on, okay, now we can use this as a substract, we can merge it with something else, we can do that in a different space with different parameters. Like this is what we'll like to see, is like how sustainable this is going to be going forward. So it's really really exciting.
I have to say that compared to this study, the weir in practice is really like complicated. When we see the failure part, it's usually like more than one mechanism leads to this material failure. So it's really complex, but I have to say it's really interesting.
And is that is always the case? Like in all the cases that I have been working in 22 years in in corrosion and integrity, it's very rare that we have only one mechanism acting.
Definitely.
It's a combination of things, and often we need to assess the impact and the risk of one mechanism over the other, because when they merge together, it's like party of madness happening into our poor alloy. But it is, like you said, it's at least it addresses this one portion that is the wear and erosion, and then all the other components will come up on top of that.
Yeah. Even not weir itself, it can even combine with corrosion to cause the failure of the material.
Totally, totally. Yeah, we had someone in the podcast that came and said that almost everything that fails has a fatigue component. And almost everything that fails that has fatigue also has some sort of corrosion or degradation mechanism that comes along with it. So it's
Yeah,
just like in the human body, right? It's not only one thing that makes you sick. It's a combination of things that ultimately lead to to lose your health, I guess.
exactly.
So this is a really cool advancement. What do you see? What do you foresee on this area, or any other in, in material science, let's say in the next 5 years or in the next 10 years? How do you see this going forward? I know that I was amazed when I was in the conference in Edmonton to see all the research and all the materials that have been studied and that are being part of people's, in the radar of people's eyes. How do you see this happening in the next 10 5 10 years?
So, for the material part, so high entropy alloys, as I already introduced, high entropy alloys are gaining a lot of attention due to their superior properties, their unique properties compared to conventional alloys, including its enhanced resistance to wear and erosion. There are a lot of studies working on high entropy alloys, and some of them working on high entropy alloy coatings, which are more cost effective. I think we can see an increased use of high entropy alloy in sectors, especially in automotive or aerospace engineering. So for manufacturing part, I think that additive manufacturing (AM) is really a hot topic. It allows us to precise control the compositions and the microstructures of the sectors, and also it allow us to tailor the properties for specific conditions, and also for AM, the cooling rate is relatively high compared to like traditional casting, so it can lead to a fine microstructure patterns, which is good, which can lead to a better strength ductility balance. So I think AM could be like a hot topic.
The way you speak about it, it makes me want to go back to school. It's really cool. So I can't not ask this question, because there is only so many female in this field, so many researchers that are female. We all know this is male-dominated world. We saw it in the conference. I was very glad to see lots of female representation. Still is way under 30%. Um, so, how has been your experience being, a researcher in this niche topic, being a female?
So, to be honest, being in the field where there are few female professors, female colleagues, makes me feel isolated sometimes. And pursuing a PhD is a long and demanding journey. And there has been moments that I question whether I'm suitable for this field, whether I'm capable of doing it in a good way. And I even doubted my ability to solve those problems. To navigate these challenges, I'm seeking out the opportunities to engage with young peers, to talk with to talk with people I met at conferences and seminars, both male and female. So our talks go beyond just academic questions. We also share difficulties, struggles, and uncertainties that come with our past. So these conversations reassure me that I'm not alone. I'm not the only one who struggle with those difficulties. I can still remember that I met a female postdoc at a conference, and we talk a lot and she told me that if you feel struggle, if you feel unhappy, go talk to another PhD student. You will find that all the difficulties you face is common. It's very common as like a PhD student. So I think being invited into this podcast is also a good opportunity for me. So thank you very much for giving me this opportunity to talk to you and share my thoughts to others. So I think those communities support me a lot, but also motivate me to contribute back to helping others who wish to join this universe, who are interested in wear and erosion.
Well, thank you so much for sharing. You know, the very purpose of the Material Business podcast is to talk about things that nobody talks. And during the technical conferences, it's nice to see all the development and look at those amazing graphs and the research that is behind everything. But we really think that we are all human, and without, like you said, we feel sometimes that we are the only ones and we are alone and we are under so much pressure. And like you said it rightly, it is some maybe just talking to someone else, you'll realize, oh, everyone is just going through the same struggle, or they did at some point in their life, in their research, in their studies, in their work, in something. So being able to and open to share without judgment, and just saying everyday like things, it really feels the purpose. So you're here today because you accepted the invite for being here. Kudos to you. You did really well.
Thank you.
And I wish for everyone or anyone that is listening that is feeling alone, reach out, because there is other people, other females, other males, other people that are minorities that have certainly gone through something, and just sharing that story may just make you feel better in a way. So reach out if you haven't.
Yeah, I know that sometimes it's difficult to start a conversation. It's difficult to like say hello, to introduce yourself, but I think that we need to talk to someone if you feel like you're alone, you're the one like struggle. I feel like we need to talk to someone, especially those like work in the same field with you. Like we are like very more than glad to support each other.
Definitely, definitely. And that's what makes us a better, that is what is will make this field be better, that we are opening to those conversations, and we are opening to say, hey, I also went through that, no worries, this is how I coped with it. I don't know if it will help you, but I it helped me. So, and then you talk to 10 people, and 10 people will share their stories, and then you will feel different. So you said it sometimes it's difficult to say, hey, hello, I'm having this struggle. Like, is there any tip that you can leave the audience? How have you faced that? Like, gone out of your comfort zone and say, okay, I need to do this. How, like, what are your, any tips?
So I think first you have to keep this in mind that the people around you are really nice and they always willing to help you. You have to keep in mind. You don't have to force yourself. I think it just happened. You just say hello and people wish to talk and people are glad and wish to talk to you because it not only ends like in academia that we share thoughts, we share our findings, but I think people also willing to share our difficulties and wish to share those uh, how to solve those problems. I talked to some female professors and they gave me like many advices like how to deal with the difficulties, how to deal with the advances in their careers. I think you just relax and talk to people. That's important.
Yeah. Another girl that came to the podcast, she said that. She said, cut yourself some slack and don't be just so hard on yourself, and be open to open up, and then just say hi, and if the person goes back, it's okay. If not, maybe that wasn't meant to be at that moment, and you'll find someone else.
Yeah,
So also it's important not to take it so personal and say, okay, now she didn't say back anything, like, should I just not do it? No, just keep trying, and
yeah,
you'll find the person that fits your purpose in this journey.
exactly.
Wandong, thank you so much. It's been beautiful having you here. Thank you for
Thank
sharing with
you.
so much passion and, having all those examples to give us real comparison to real life, and then for opening up and being vulnerable. It's also very nice to have that portion. Any last words for the audience? Let's say someone wants to go into research, or there's a little girl in high school that wants to be engineer, or like, what will you be your message for the audience?
So for those who wish to start in material science for those who wish to start in engineering, I highly suggest you to attend conferences, join professional societies, participating in some workshops. You can listen you can hear the thoughts from others, and also you can share your own thoughts, your own results with others. It's really important, and you can gain insight into the current state of the research and also the future direction, which is also important. I also wish to talk something about weir. So weir is, I have to say, it's very like old topic, but it's really interesting. So erosion, as I mentioned today, is just one of the types of weir. So there are many of them. For example, adhesion, abrasion, fainting weir. So I have to say that don't be like scared to work in industry or work in engineering. It's really complex, but it's really worth to exploit, worth to contribute your time, your passions into it.
Amazing. I could have not said it better. So if this is your passion, go for it. And there is nothing that will stop you. And then reach out for collaboration, because more people will say yes than you ever think they would. So, and this is what happened today. I reached out and she said yes. And here we are recording this beautiful podcast. So thank you for being here, Wanda. Thank you for sharing your expertise, your passion. Thank you for all you do. And hopefully we'll get next opportunities of collaboration.
Thank you so much. Thank you for inviting me again. Thank you.
So, for all the audience, we'll see you in the next episode of Material Business. Thank you so much and keep posted.